Hello students, you're welcome to our physics lesson, and specifically we're going to look at this topic of waves, and majorly we shall tackle the applications of Fermat's principle. Fermat's principle has got like two applications, and that is deriving the mirror and less formula. Also we shall look at proving the laws of reflection and refraction. Basically, out of those applications, we're going to concentrate on proving the law of reflection. Fermat's principle, we need to know that this is whereby the path taken by a light wave between 2 points, such that the time that that wave takes is the minimum. For example, we have 2 points, maybe point A and point B, and we have a light wave, maybe it can be light, traveling from point A to point B. Now, under Fermat's principle, the time that this light wave will take to move from point A to point B, it is the minimum, okay? Now, we are going to see how we can use this Fermat's principle to derive the law of reflection. And basically, we shall consider a mirror. We'll consider a plain mirror. This is a plain mirror, such that a certain ray of light is incident on this mirror, maybe from point A, and then it is incident at this point A, from point O to point A. And of course, you know the principles of plane mirrors. When a ray is incident on the mirror, it must be reflected. Now, suppose this ray is reflected along maybe AB, such that we need to have a normal. This is our normal. Now, we need to ensure that this angle of incidence, theta 1, maybe theta 1, is equal to the angle of reflection, maybe theta 2. So that's the law that we want to prove. We want to show that theta 1 is equal to theta 2 using the law of Fermat's principle. Now, after having that diagram, suppose we have our height here from the initial point of the ray, where the ray came from, and then maybe we can call it H1. We also have another height here. We can call it H2. Now, if we assume that the horizontal distance is maybe from here up to this point, suppose it is distance D, that is the point from this first point up to this, okay? Now, suppose the distance from this point up to A is x. If this is distance x, this is our distance x. So meaning that this distance, if we want to determine this, we shall get d minus x. So this is, this will be d minus x. So that will be our distance from point A up to this point. Now, we need to find what we call the optical path, because we need, you know that from Fermat's principle, the optical path, if we differentiate our optical path, maybe if it is L, and if you get the L dx, we differentiate the optical path L with respect to the horizontal distances, maybe x, this one must give us a 0, because Fermat's principle, we need to ensure that we get the minimum time taken by a ray moving between 2 points. Now, how do we get the optical path? From optical path, it is given by the refractive index, then multiplied by the path length. Remember, when this ray moves from point, maybe from here, maybe this is distance capital D. So for this ray to move from here to here, it will pass through this route from O to A, then from A to D. So that one will be the optical length, okay? Now to get the optical path, we shall get the refractive index. For example, suppose this is N1, that is the refractive index at that point, and maybe this is N2. So we shall multiply the refractive index, then times the optical path, or you can call it path length. Path length. Now, how do we get the path length? Of course, our path length will be the distance from O to A, and then we add it to the distance from A to D. That will be the path taken by a ray of light moving from point O up to point D. So our path length will be OA, then plus AD. Now, how do we get OA? When you look at this right angled triangle, if we use Pythagoras theorem, of course we shall get the square of this plus the square of this is equal to the square of this. So to determine this, let me show you clearly. And then I want to determine this distance. This is our x. This is x. And also this is distance h1. So if I want to determine this, of course it will be, suppose this is y. From Pythagoras theorem, our y squared will be x squared plus h1 squared. So our y will be the root of x squared plus h1 squared. So meaning that this distance will be the square root of h1, then plus h1 squared, then plus x squared. Plus x squared. Then it is the same case for this distance. It is given by the square of this and the square of this under a root. So this will be the square root of d minus x squared plus h2 squared. So our OA will be the root of h1 squared plus x squared. Then our AD is the root of d minus x will be the root of d minus x squared, then plus h2 squared. So that is the path length, the distance taken by a ray moving from point O to point D after being reflected at this point. So we can say that our path length is equal to, so I can put, a root is the same as power half. So this is h1 squared plus x squared power half, then plus d minus x squared plus h2 squared, the whole of this is power a half. So we said that the optical path is given by refractive index times the path length. So we have to get the optical path will be refractive index n1 times the path length from O to A. So we shall get n1 times OA. So our OA is this one, which is h1 squared plus x squared power a half, then plus n2 times d minus x squared plus h2 squared power half. So from Fermat's principle, when you get the derivative, when you differentiate the optical path with respect to x, we shall get 0. We equate it to 0 after differentiating. So we say from the LO, actually here we should have said that our optical path, maybe it is LO. We can name it LO. So our dLO dx is 0. So we are differentiating this and then we equate it to 0. Such that when you differentiate this, our dL dx will be, we are dropping the power first. So it is a half n1 times, we reduce the power by 1 and maintain what is inside here. So h1 squared plus x squared. A half minus 1 is negative a half. Then after that we then differentiate what is inside with respect to x. So what is inside is h1 squared plus this. So when you differentiate this, we shall remain with 2x. Then plus, we come here, it will be, we are dropping the power first. So it will be a half n2 into, so here we are maintaining what is inside and then reduce the power by 1. So it will be d minus x squared plus h2 squared. So a half minus 1 is negative a half. Then we differentiate what is inside with respect to x. So when you look at this, the derivative of this, we shall drop again the power, which is 2. Reduce the power by 1, which is d minus x. Of course, 2 minus 1 we shall remain with 1 here. This is power 1. So after that, of course, the derivative of h2 squared is a 0. Because it is a constant, we are differentiating with respect to x. Then after that, we then differentiate what is inside with respect to x. Pause. So when you get the derivative of d minus x with respect to x, of course we shall get negative 1. So this is negative 1. So from there, I can drop this power negative half and I put this expression down. So my dl dx will be, this 2 will cancel with this, and I remain with the n1 divided by h1 squared plus x squared power half, then plus, this is a negative. Of course, when you drop this one, here we shall remain with this 2 will go with this, and up we shall remain with, this is negative d minus x, this one here, divided by, I'm dropping this expression, remember here we have n2, so divide by d minus x squared plus h2 squared. The whole of this is power a half. So I'm equating this expression to 0. So dl dx is 0. So when you come here, we shall have n1 over h1 squared plus x squared over half minus n2 d minus x over d minus x squared plus h2 squared power a half. So the whole of this is equal to 0. So when you look at this one, when I put this on this side, of course this one will be equal to this. But before that, remember, the ray was moving from within the same medium. Of course this is air. So the n1 is the same as n2. So n1 is equal to n2. So here I will have, remember here we forgot our x. There is x here. There is x here. Sorry for that. So we shall have x over root of h1 squared plus x squared is equal to d minus x over d minus x squared plus h2 squared under a root. So when you look at this diagram, x over root of this, it is the same as sine of theta 1. How? You know, remember this is our theta 1. So if this is theta 1, if I complete here like this, I also complete here like this. So our x is here. Now if this is theta 1, it means this one is also theta 1. Angle properties, also this is theta 2. So this is opposite and this is hypotenuse. You know that sine opposite and hypotenuse. So this is sine theta 1, which is the same as sine theta 2. This one is sine theta 2. When you look at this is opposite and this is hypotenuse. But you know that for small angles, my sine theta 1, this one tends to theta 1. Also, sine theta 2 tends to theta 2. So implying that theta 1 is equal to theta 2. And remember, we said that our theta 1 is the angle of incidence, and also theta 2 is the angle of reflection. And this shows that we have proved the law of reflection, because the angle of incidence is always equal to the angle of reflection. So that's how we use the Fermat's principle when we are proving the law of reflection. In our next lesson, we shall see how we can prove the law of refraction using Fermat's principle. Thanks for watching.